Yeah. Yes. Okay, so we can see your screen and we can also still see you. So I'm just checking if we can start here. Just tell me yes. Yes? Okay, so then let me introduce our next very interesting speaker. So we have here Michaela Blott, who is a distinguished engineer at Xilinx Research in Dublin, Ireland, where she heads a team of international scientists driving exciting research to define new application domains for Xilinx devices, such as machine learning in both embedded and hyperscale deployments. She's also very active in the academic community, so organizing conferences, workshops, being chair of conferences and workshops, in EU projects, being a member of technical program committees, etc. And she was also the winner of the WMB Award in 2015, finalist of Venture Beat Women in AI in 2019, and Women in Technology 2019. So I'm very happy to give her the word. So please, Michaela, go ahead.
Well, thanks so much for the kind introduction, and hello, everyone. It's great to be part of the event, even if it's just virtually. And I have my hopes out now for 2022 that we'll finally be able to meet people in the real world. So I thought I'll be talking to you today about innovative approaches to AI acceleration. It is a subject I've been personally working on now for many years, of course, in the context of FPGAs. And if you don't know what FPGAs are, don't worry, I'll introduce everything. But the ideas are actually far more general. But before we get to this, I'd like to start with a bit of background about Xilinx, and I've also been asked to include a bit of background to myself, so you get a bit of that at the beginning. Okay, so Xilinx is the company that I work for. It's a fabless semiconductor company, about 30 years old. It was originally founded in Silicon Valley in 1984 and is today about 4,000 employees and $3 billion of revenue. So in the future, this slide will say AMD on this. Our closing date of the impending AMD acquisition is any day now, so it's imminent. But right now we're still Xilinx. And Xilinx itself is probably most famous for inventing the FPGA, which brings me to the next slide. So I'm not sure how many of you know what FPGAs are, so I thought I'll just do a quick introduction to make sure everyone can follow the rest of the talk. So FPGAs are in essence the customizable, programmable hardware architectures. I would call them the chameleon amongst the semiconductors because they can change everything, right? You can customize the I/O interfaces on the chip. You can customize the compute architecture, the memory subsystems. You can do exactly what is required by the application. And the use case for this is you have a system, a printed circuit board like the one shown here in the picture, and nothing else works. And you really do not want to do your hand custom designed ASIC implementation. Then you plug an FPGA in there. So the FPGA will be able to support you with non-standard IOs. It can offer you different functionality to anything that's available on the market, and it can achieve higher performance or efficiency metrics through customized hardware architectures. And that's actually something we leverage in the context of AI, as you will see on later slides. Now, last slide about FPGAs, just to explain to you what they actually consist of. So they are in essence a sea of lookup tables, like you can see here in the picture. We call these lookup tables slots for shorts. The latest device will have millions of them, so they've been consistently getting bigger over the last years. And these are interconnected with a programmable interconnect, which has a very high cross-sectional bandwidth. We have programmable I/O, as mentioned on the previous slide. And with more recent generations, we have novel compute elements such as DSPs, which carry out n-bit multiply accumulates, and embedded on-chip memory in form of SRAM. And that's in essence what comprises one compute die, a monolithic FPGA. And what more recent generations do, they leverage what's called stacked silicon interconnect technology, where one basically packages multiple dies together and add them on top of a silicon interposer, which provides the cross connectivity. And this helps with scaling the capacity of the devices. In the future, we're going to go probably more 3D, which is an industry trend. But right now it's kind of, they call it 2.5D. So I'm heading the Xilinx research organization in the European headquarters here in Dublin. This lab was established 15 years ago and is now, roughly speaking, around 7 full-time researchers plus a university program. And the work I'm showing here is representing the work of these amazing researchers, and I'd like to name them because they do all the work. So Nick Fraser, Ken O'Brien, Alessandro Pappalardo, Lucian Petrica, and Yaman Omuroglu. Our main charter here is quantifying the value of our devices in machine learning, whereby our approach is really hands-on. So we're building full systems, we're exploring different hardware architectures, and we're doing a lot of optimizations on the algorithm level. And finally, important to say, we're operating typically in close collaboration. So we're working inside of Xilinx very closely with engineering and marketing and sales. And externally, we work very closely with universities, for example, ETH Zurich, Delft University, Heidelberg, Politecnico di Milano, Paderborn, Darmstadt, just to name a few. And we also work with customers. For example, we've worked with Daimler on quantization of the neural networks for a gesture recognition system, which is in their V-class model. So very cool applications. Okay, so that's what I wanted to give you a background on Xilinx. Now a bit on my personal background. You probably told by my accent meanwhile that I'm German myself, and I grew up in a small town by the name of Ida Oberstein. Maybe some of you know it. It doesn't have a motorway connection, and it's about an hour to any big city around it. It's basically in the middle of nowhere, at least in my opinion. So when we talk about what motivated me actually to go for an engineering career, I always liked technology, but the reason why I went for an engineering career was different. And the number one reason was actually to get away from Ida Oberstein. I really wanted to go see the world, and I knew engineers and computer scientists are needed everywhere. So I thought, this is my ticket out of here. So that was the first reason. And the second reason why I wanted to be an engineer, because I wanted to earn my own money. I wanted to stand on my own feet and not depend on a husband who's going to tell me what I can and cannot do. So that was really important to me. And I knew engineering careers, engineers are going to be well paid and sought after everywhere. And then finally, and perhaps not very mature, but I had a rebellious streak, and I really wanted to be mostly different. And so that's what kind of got me started to think on an engineering career. And what manifested it was when we had the career counseling in the last year in high school, and they asked, what do you want to do after school? I said, I want to be an engineer. And I was told that's not possible because only boys can be engineers. And there and then I decided that I will have to show them, and I have to become an engineer. Anyway, I'll come back to this later on. But what evolved afterwards was a master's in computer science, NEE, at the University of Kaiserslautern. Admittedly, this was only 1 hour drive away from Ida Oberstein, so I didn't get too far away. But after that, I ventured further to the ETH Zurich in Switzerland, where I was lucky enough to work as a research assistant progressing a PhD, which then I dropped about 3 years in as my supervisor left the university. And I thought at the time, who needs a PhD anyhow? It's something I regretted later on, but I went then to the US to join Lucent Technologies. So I did go get out of Europe eventually. And I joined Bell Labs, where I worked as a researcher. And also importantly, I had 2 kids during the time in the US. And then we moved to Dublin, where I'm located ever since. That was actually not the plan. I only wanted to stay a year, but it ended up being 18 years meanwhile. It's not a bad place. And I worked first in a startup company where I progressed from a developer to a head of development, which was very fun, working mostly on electronics for airspace. So there was lots of design work. And then from there, I jumped to Xilinx, and as they decided to start a research operation in the European headquarters. And I always had a preference for working in research over development. I always wanted to play with the latest technology. And so I was delighted when that became an option. And I was actually the first one to get hired into the Xilinx research lab in Dublin. And here I've slowly progressed from researcher to most recently fellow, which is equivalent to a vice president on the technical career ladder. So this is well beyond what I thought I ever get to. And as Neda said, I'm heading here the European Research Lab meanwhile. I was also productive in the private space and added 2 more kids to a total of 4. And perhaps my last milestone was that I completed a PhD part-time earlier this year, thank goodness, because it was always something that's been nagging at me ever since I dropped it in my earlier career. So that's basically the summary of my own personal journey, which brought me to here today. So that's all the background. Let's dive into the actual research now that we've been carrying out here. And I'd like to begin with a bit of overall context. So why are we talking at all about innovative approaches to AI acceleration? What's driving this need? So the need comes basically from machine learning in the form of deep neural networks, which are emerging absolutely everywhere because they come with such a huge potential. The first part on why they are so popular is because it requires no domain expertise to solve problems with neural networks. So you can solve problems with neural networks that you don't understand yourself. So that's a big deal. And then secondly, neural networks are popular because they're universally applicable. You can basically throw them at any problem. And finally, if you make the neural network big enough and you train it with enough hard data, then it can actually outperform humans and existing algorithms. So it can get more accurate solutions. So that's a big deal. The famous example here was from 2012, the ImageNet classification context, but there's all the time new examples emerging. So there's basically 2 profound consequences out of this. First of all, the number of applications will keep on growing as neural networks replace existing implementations, and we observe this everywhere. And secondly, DNNs will solve previously unsolved problems. So famous example from end of last year was the AlphaFold by DeepMind, which allows the prediction of protein construction. That was actually a grand challenge in computational biology. Humans hadn't solved this for 50 years, and now here we go with neural networks. And there was another example, which is perhaps more in the first category, where the DNNs published in the Nature journal outperform existing rain prediction algorithms. This is super important when you live in a place like Ireland and you actually get to know when you can leave the umbrella at home. Okay, so however, them being so incredibly powerful, from a computational point of view, neural networks are really simple. So if you know this already, please stay with me. It's just 2 minutes worth of background and make sure I'm not losing anyone during the later part of the presentation. So DNNs are usually feed-forward computational graphs constructed from one to many layers, like shown up here. There can be up to thousands, and there are many different topologies used. Now, each layer in the DNN consists of neurons, which are interconnected to the neurons in the previous layer through so-called synapses, whereby each synapse has an associated weight, which determines on how heavy this input features in the calculation of the subsequent neuron. So in the neuron computes a dot product out of the synaptic weights multiplied with the value of the neuron in the previous function. So it's just a weighted sum. And this is then fed into a nonlinearity, which acts as the activation function and the output of what is the value of the neuron. Before I can deploy my neural network, we need to train it. And for this, we basically random initialize all the weights in the neural network, and we expose it to a training data set. And for each of the images in the training data set, I know what's in the image. So I've labeled outputs for this. So what I do then is I just propagate my training data through the neural network and see what comes out of it. And then I do a comparison with the actual labels and determine how far I was off it, right? So how much error did I have? And if the error is too high, then I will go back propagate the error through the neural network, adjust my weights, and then try again. So I do this iteratively until eventually I have sufficient accuracy achieved, and then my neural network is ready for deployment, which is also called inference. In the inference scenario, the DNN is then exposed to a new previously unseen input and hopefully gets it right then. So overall, it's a really simple concept and very simple to compute. So because they're so simple and so powerful, they've meanwhile been key to enabling, in particular, machine perception. They are used in many computer vision tasks, from image classification to object detection and so forth. They're also being adopted in speech recognition. Think of Alexa and Siri, and this whole interface with operating on voice command will become much popular, because it's just way easier to talk to your computer and devices rather than typing and pushing buttons. And finally, natural language processing is taking off big time. For example, translation services. Where would we be without Google Translate, as well as sentiment analysis, for example, to judge the quality of service on a customer service hotline. DNNs are also key in solving the big data problem. We are drowning in data. Planet Earth is generating astronomically growing amounts of data as we deploy more and more sensors. Think of your Fitbits and your various other health monitors. We have more and more users and more applications. I always thought we're going to drown in YouTube videos, but it's actually not true. We're actually going to drown in DNA, which is used not only for resurrecting dinosaurs, but more seriously in archaeology and space research, family tree tracing, paternity testing. It's used for medical, of course, to identify genetic diseases, and for crime investigations. So machine learning will be the way to digest this huge amount of data and extract intelligence and know-how from it. And beyond these popular applications in regards to machine perception and knowledge distillation, we see many new machine learning applications emerging, in particular in communications, such as network intrusion detection that Nele would know about, but also medicine, drug discovery, high energy particle physics, even EDA. Maybe you heard the Synopsys keynote at Hot Chips, really cool stuff, having AI design new chips. So it's popping up everywhere. So what's interesting about these new use cases is that they can have very different latency and throughput requirements. For example, state-of-the-art ImageNet classification with ResNet 50, which is a very popular topology, in 2020 shows the best numbers. It's tens of thousands of inferences per second. Now in the communication space and particle physics, you need hundreds of millions of inferences per second. So an upshot is there are many new applications, and not only many more applications, but also rising performance requirements that come with it. So at the same time, the compute requirements are growing in deep neural networks at an incredible pace too. So here shown in the chart, y-axis is compute in petaflops on a logarithmic scale. X-axis is chronological, so in years. And what you can see here is that the compute requirements on the red line has doubled every 3.4 months, according to OpenAI. So doubling every 3.4 months. And as you know, Moore's law offers us doubling performance every 18 months. So even if we were progressing with Moore's law, there would be a widening gap in terms of compute requirements that we in the semiconductor industry can't easily fill. But you know what, that was only while Moore's law was live and kicking. And as you know, this hasn't really been the case in recent years as we're approaching the really small technology nodes such as 3 nanometers. So it's even worse. So there's not only the black gap, but there's also the red gap forming. It's double whammy. So that's the challenge that you're facing. And as a result, innovation is needed to make this happen. So we need innovation to build hardware architectures that it can accelerate the emerging DNN workloads and enable all these new cool applications that are coming. So from a computer architecture point of view, this has been incredibly exciting in recent years and still is. There's a lot of innovative and exciting approaches happening, from Cerebrus wafer scale computing, which built the chips as big as your dinner plates, to 3D die stacking, packing multiple dies on top of each other, to quantum computing and analog computing. And in this talk, we'll focus on the less exciting approaches, but these are the more realistic approaches, which leverage specialization in the computer architecture to achieve the required performance scalability. And I'll refer to these as deep learning processor units, or DPU for short, but others might call them IPU for inference processing units, TPU for tensor processing units, NPU for neural network processing units, or stimulate. So we're just going to agree for this talk, we're going to call it DPU. And there are many startups operating in this space, such as Habana, Nabana, Sambanova, and Graphcore. I almost have to add a new one every other week here. But in addition, there are also hyperscalers building their own. Google's TPU is very famous, but all the others are doing it too. So AWS has Inferentia, Huawei has the Ascend processor, and even in the automotive space, Tesla is building its own custom silicon. So I'll zoom into the DPUs now, but before going there, let me also say a few words about GPUs, which play, of course, a major role in the acceleration of machine learning workloads. I used to have GPUs listed as a separate category, but the lines are really getting blurred as GPUs are now also increasingly specializing for machine learning workloads. So let's dive into the DPUs now. So the ones that I cover here are just the ones that we've been working on in my team. I just want to acknowledge here for a moment that there are many other cool ideas in the community being investigated, but these ones are the ones I can cover best. So we classify the DPUs by their degree of specialization from left to right, whereby the most specialized devices are the ones furthest to the right and the most generic ones are to the left. And with the increasing specialization, as you'd expect, we get improved performance and increased efficiency. So we identified 3 categories here, but there are no hard boundaries in between. In reality, this is a fluid spectrum. So on the far left, we have the first category, which customizes for DNNs in general. And the architecture consists typically of a matrix of processing engines, and I call them MPE for short, and I'll explain that in the coming slides. The middle category we call streaming data flow processors, or DF for short. These customize to the specifics of a topology. So this is any neural network. These are only specific topologies, okay? And on the far right, we have the extreme variant where we're no longer running a neural network and accelerating a topology in the hardware, but the circuit becomes the neural network. So the topologies are in essence fully co-designed for the hardware architecture. So I'll go through these individual categories now in more detail, starting with the matrix of processing engines first. So a matrix of processing engines, they look something like this. We have a chip with a matrix of processing engines, like the name says, whereby each processing engine could be multiply, accumulate, as simple as that, or it could be a VLIW processor, a vector processor, doesn't really matter. We have, in addition to the processing capabilities, on-chip memory buffering, a DMA, and an external memory subsystem. And this is, of course, strongly simplified, but you will find that many of the startups will operate in this space. So we refer to these architectures as a layer by layer compute because of the way they execute a DNN inference is they load a batch of input images onto the device, then schedule the compute of the first layer, buffer the results, then execute the second layer, buffer the results, and so on and so forth. So they iteratively process all of the layers. Batching, or the processing of multiple inputs in parallel, is really important here to achieve compute efficiency. For example, if your first layer had only enough compute for 4 engines, so one layer occupies only 4 engines, then I would only have 25% compute utilization. So what I do is I process a batch of 4 input images at the same time to get a higher utilization on the processor. The problem with the batching is that it comes at the expense of latency, right? Because I have to wait now until I have 4 images per cent. Only then I can execute over the layers, right? So if latency is proportional to the batch size, as I need to buffer all incoming images until they're fully assembled. So if you look at Jan LeCun's keynote at ISSCC 2019, one of his big wishes from chip makers was performance without batching. So these architectures are customized by specializing for processing engines, in that they only support the operators that are required in the DNNs. So for example, multiply, accumulates. And they also specialize in the types of ALUs that they have. For example, they have tensor ALUs, matrix, or vector-based ALUs, okay? But they are customized for machine learning in general and can execute any workload in principle as long as the operations are supported in the hardware. So this degree of specialization is popular with the dedicated silicon approaches. For example, the TPU would roughly fall into this category, as well as many of the startups, like I said. So in summary, MPEs can cater for a broad range of applications with one highly optimized architecture. Works really well for computer vision and natural language processing. So now on to the next category, the data flow processors, or DF for short. And the tricks we're using here are streaming data flow, reduced precision, and fine granular sparsity. And I'll show that now in more detail. So with data flow architectures, we can specialize for individual DNNs through customized architectures, where we customize not only for the operations in the DNN, but also for the connectivity in the given DNN. The DNN is in essence co-created inside the device, for example, in an FPGA, and all layers have dedicated compute resources in the device, whereby the compute resources between the hardware and the requirements is proportional. The inputs are then just streamed through the architecture. It's like a pipeline processor, okay? So this extreme specialization brings advantages over the MPE. First of all, efficiency. We only instantiate what's needed, right? This is exactly what's in the neural network. It's better in latency. We don't need to buffer before and after the layers, no batching required. And finally, either lower resources or higher throughput. So with data flow architectures, I can scale the resource footprint down to fit into really small devices by removing compute resources from each layer proportionally. Or conversely, I can scale it up to run at much higher throughput by adding more and more compute resources proportionally to my layers. And if I have enough resources, I can fully unroll my DNN in the FPGA. What that means is every operation in my DNN will have dedicated hardware resources. And at this stage, my architecture will run at maximum speed and classify a clock rate. So if my design clock's at 200 megahertz, this will give me 200 million inference per second. And so this is how I can achieve extreme high throughput for these emerging applications, such as we see in the communication space. By the way, when it's fully unfolded, we talk about fold 1, and the nomenclature is fold X is basically 1x of the throughput, of the maximum throughput that I can achieve. So upshot here is the architecture can scale performance to meet these new requirements by specializing to a much greater extent than with the MPEs. Okay, so that was the first trick. Now onto the second trick, which is the second form of customization, is exploiting reducing data type precision. It's quite a popular idea to basically reduce the data types during training of the DNN as much as possible while still achieving sufficient accuracy for my application. So here are the benefits that I get from this. So first of all, it uses my hardware resource. For example, if I reduce my multiply accumulate from operating at 8-bit to 1-bit, the hardware footprint of this operator shrinks by, roughly speaking, 70x. And when I shrink my compute operator, that means I can instantiate many more of them, which translates directly into performance scalability. The second benefit is that it reduces my memory footprint for the weights in my DNN. So let's use the ResNet 50 example again, which has 25 million weights. If I store them at 32-bit, then I need over 100 megabytes. If I just store it at 1-bit per parameter, then I only need 3 megabytes, which is something I can store on chip and avoid any potential memory bottlenecks. Also worth noting, as every layer has dedicated compute resources, we can mix and match position across layers, and with that exploit custom arithmetic at a greater degree than MPEs. So, and finally, it also saves power. I won't elaborate on it here, but it should be intuitively clear too. So there are massive benefits that I get from reducing precision, namely performance, resources, power, and memory, which we can exploit with these custom architectures. However, it requires quantization support in the training of the neural network. So the third form of customization that we can leverage is pruning. And the idea is basically to leverage pruning of all synaptic connections where the synaptic weight is below a certain threshold. So once that synaptic weight is sufficiently small, we know that that neuron is not contribute much into the dot product of the next neuron. Therefore, we might as well remove it. So here's shown an example in the picture between the original DNN and the pruned sparse DNN representation. So what this does is, of course, dramatically reduces the compute load of the neural network. So sometimes you can reduce it down to 10% of the operations that you had in the original network. So the resulting topology in its most extreme form, however, will have irregular sparsity, as is shown here on the top right here. So irregular sparse topologies result in irregular compute patterns, which are, of course, difficult to parallelize and therefore hard to accelerate with vector or matrix-based execution units such as the MPEs. If you remember, they often leverage tensor or matrix or vector-based ALUs. So with streaming data flow, as shown in the lower two figures, it's different. So here you can see each layer and each neuron is represented in the hardware, where in this case, the neural network is fully unrolled here. So every neuron synapse is represented in hardware. When that's the case, then I can take full advantage of the granular sparsity because I can just individually remove the ones that have been removed during the pruning process. And what's more so, now for those of you who are FPGA savvy, for FPGAs, the hardware synthesis process will automatically remove them when the weights are set to 0. So it's actually a benefit that will come for free. Okay, so you thought this was extreme, but we can actually still go further, and that's what we do with the variant on the far right, where my topology is fully co-designed with my hardware architecture. In essence here, I'm no longer specializing my hardware for the DNN, but it's the other way around. The circuit, the hardware circuit becomes the neural network. And we refer to this project as LogicNet, and I'll explain that now in a little bit more detail. So the main idea behind LogicNet is that a lookup table in your typical FPGA fabric, I hope you remember the start of the presentation. So these LUTs can be identical to a neuron. So our lookup tables always have 6 input bits. So any neuron which has 6 binary inputs, it can have floating point weights, batch norm, threshold activation function, but with a binary output, this one here can be equivalent to a lookup table. And by the way, there are ways to scale this to more inputs and higher precisions inputs and outputs, but let's keep it simple for now. With this, we can then turn the whole problem on its head. So up until now, what we did was we pick a neural network, it gets trained for a specific task, whereby during the training process, remember, we adjust the parameters of the DNN while iterating on the training data set until desired accuracy is achieved. And then we take it and we optimize the hardware for it and deploy it. With LogicNet, we can do it the other way around. So we start with the circuit and assume that it's an unrolled DNN. And this DNN, by the way, is naturally sparse to suit the limited fan-in of the lookup table and the interconnect in the FPGA. And then we train this DNN, whereby during the training process, we adjust the parameters of the neural network until we achieve the desired accuracy, whereby the parameters directly map onto the lookup table contents now. And then you can deploy it whereby the circuit is maximum performance by design and will classify clock rate. So you might wonder.
You have five minutes, if possible.
Ooh.
Thanks a lot.
Okay. Yeah, I'm getting there. All right. And at this stage, it's maximum performance by design and will classify it clock rate. Okay, so I'm going to skip a little bit. So if you look now at these spectrums of DPUs, they can be built either with FPGAs or with dedicated silicon approaches. There are some basics here at play that you might be familiar with, and I'm trying to visualize this in this chart with a simplified way. So if you look at this chart, it shows cost to produce a specific volume of devices, whereby with dedicated silicon devices, and I call them ASSPs here, could think of them as ASICs, I have initially a very high NRE, but then as I go into volume production, it gets cheaper. And for FPGAs, it's the opposite. So the NRE is much lower, but the device cost is higher. So the increasing the volume, the line rises faster. And then you have the well-known crossover point. So when you're to the left of this point, it makes sense to stick with FPGAs from a cost point of view. And to the right, it makes sense to build an ASSP. And this applies to deep learning as every other application. So now as I start specializing my architecture for DNNs, the potential sales volume decreases and it becomes hard to amortize the cost of the device. And that's when FPGAs make sense. For example, nobody would build an accelerator just for ResNet 50. So let's take a look at performance versus specialization in the second chart. So increasing the specialization improves the performance, right, as you go to the right. However, the potential sales volume decreases as I'm specializing, and it becomes harder to amortize the cost of the device. And that's when FPGA makes sense. For example, nobody, right, would do the ResNet 50 accelerator like I previously mentioned. So with increasing specialization, I get improved performance. The more I customize my device, the more performance I will get out of it. And what's the upshot here is that once you get beyond the crossover point, it actually is the opportunity for FPGA. So once I increase the specialization degree, I will get more performance out of my FPGA, which makes it worth my while. So that's the opportunity for FPGA devices in the ability to specialize through the programmable interconnect, the precision, the programmable operators, and so forth. Okay, so there's a, I have to skip quite a bit. I don't know where the time went. So I was just going and demonstrating an example on how much you can actually performance gain you can get through these different forms of specializations. And you'll have to take my word of it now that there is a lot that can be done. And then I come to the end. So looking back over my career, did I get out of it what I hoped? And I certainly got away, right? I didn't quite make it to Asia, but in Australia, but there's still plenty of opportunity. And honestly, nowadays, I'm also happy to go back to Oberstein to visit my parents. It's actually a lovely place in retrospective. I'm certainly independent, which is essential to me, even though I'm happily married with 4 kids, and there's a limit to how independent I can be in everything I'm doing. And I'm perhaps a little bit different, although that doesn't really matter to me anymore. But what I didn't bargain for, and what I think is way more important, is that the engineering career gave me the daily workout for my brain that I actually need. I get to work with smart and inspiring people. And finally, I got to work on cool and relevant technology, such as innovative computer architectures for acceleration of AI. So talking about the technology side, there's so much happening right now. As I showed you in the slides, there's a whole spectrum of innovative architectures emerging to help with the rollout of AI technology. With specialized solutions, I can scale performance beyond Moore's law and make these applications possible. I didn't show you my network intrusion detection example, but you can get orders of magnitude improvement through these different forms of specializations. However, we need tools that automate the specialization, and we work very heavily on building open source infrastructure together. And I really think that together through an open source community, we can advance and accelerate the innovation collectively in our field. So let me conclude by saying that this is a vast field of research and that there are not enough research engineers in the world altogether. So we should really leverage open source and community efforts to make the difference here. And with that, I'm at the end, and I'm so sorry that it ended up being a little bit rushed. I thought I would have way more time for this. I'm more than happy to answer questions.
Thank you. My microphone on? Yes. Are there any questions in the audience or online for Michaela?
Hello, Michaela. It's Mihai Moldovan from Romania. I was curious about a personal question. You mentioned you regretted not finishing PhD studies when you started them. Can you elaborate, like, why, what did you regret? Like, I know if you have a PhD, you get a higher salary, for example. So is it because of that, or like because you had it in the mind to finish it?
No, I think it was more in my mind. I honestly think, you know, if I look at my colleagues at the same level, some have PhDs, some don't. I think the PhD is really great for actually enabling you the research career. So I think it's quite hard to get into a research lab if you don't do some form of advanced study. But once you're in, I don't think it matters anymore. For me, it was more kind of a personal thing. I think I like to have things finished. And when I ditched it, I thought, God, I don't need it. And then I ended up getting into a research lab and in particular Bell Labs anyhow, because I think people were desperate at the stage for researchers. It was more kind of a personal thing that maybe it was my midlife crisis. Maybe it was, you know, I'm helping people in my lab the whole time doing PhDs. I'm publishing the whole time. And then I thought, you know, I might as well do it myself. Are you doing a PhD, Mihai?
Okay, thanks. Actually, no, I just started the master's.
Okay.
Yeah, thanks.
No problem.
Thank you. Okay, I see. Thanks, yeah, for the question and for the. And yeah, there's one question in the audience. Yes.
Hello. Okay, I can be heard. You saw the slide that basically. Okay, below. You saw the slide, the previous slide about those LUTs, that if you consider it like an LUT, our design, our system will be a little like this. Is it something that you have in the future that will go from generic FPGAs to boards that are already implemented your designs, specific designs for DNNs on it?
Yeah,
it is.
Yeah. I'm afraid I ran out of time to show you this, but we've actually developed a tool called Fin. Let me just skip. It's not too far away. Here. So this is Fin. What Fin does, it has 3 components. The first part is a training library. It's a PyTorch library that allows you to do the algorithmic optimization. And it has a hardware compiler, which will actually generate these custom data flow designs with quantization implemented and potentially sparsity. So it'll automatically generate the hardware design, which you then can plug into the backend tools. And then we have a number of hardware platforms which have been pre-configured. So you can just run the neural network there, and we're leveraging Python APIs. So it's really easy to use.
Thank you very much.
Okay, thanks. More questions? Maybe I can end with one small question. So you said in the beginning of your presentation that if you make your neural network big enough, you can solve any problem and even do better than humans. I can imagine that there's also neural networks that do not fit in one FPGA, and Fin is made for like building or implementing neural networks on one FPGA. So are you also looking at clusters of FPGAs to solve larger problems?
Yeah. We've built first implementations now, which will, we've published it too, which will do multi-node data flow implementations. And Nele, it's a really important question that you're asking. In particular with this trend of neural networks. So because the bigger you make, the more you can achieve with them. Because of that, we see many more neural networks emerging, which are even bigger, and they're getting so big that you can't even fit them on a single node. You need actually 100 CPU nodes to fit the largest transformer neural networks, or you need over 500 GPUs because they even have a smaller memory footprint. So this networking capability is absolutely essential for the future.
Okay, thanks a lot. So I think that's it for the questions. So thank you very much for giving this interesting presentation.